Well, thank you all for coming today to our final Applied Quantitative and Psychometric Series talk of the year. David Dueber, doctoral candidate in Quantitative and Psychometric Methods, and Danny Rosenkrantz, a doctoral candidate in Counseling Psychology. So in this last talk, Danny and David are going to sort of put together a discussion about what we've been talking about for almost about half a year to a year or so, in terms of these techniques that can be used for measurement error correction. Without further ado, I'm going to turn it over to David and Danny.
All right, so today we're going to be using a subset of data from my dissertation study. It was an online survey for parents of LGBT children, and there were measures of cognitive flexibility, emotional regulation, parental sanctification, religious fundamentalism, and our outcome variable, parental acceptance. In the end, for this subset of data is 470 participants.
So 470 complete cases. Does that mean that everyone in your sample filled in every item for every scale?
Absolutely not. So my total N is 663 parents of LGBT children. But for the purposes of this presentation, we are only using complete cases.
We're doing that to make the analyses easier to run and interpret. It makes things simpler, but we strongly recommend that you do not delete your cases with missing data. So there are good ways of handling that in all of the analyses that we're going to be showing you today. I'll be recording a second presentation a little bit later explaining some of those more advanced modeling ins and outs of how to do that modeling.
So this is a multiple regression model. So you see all the different predictor variables here, and they are predicting our outcome variable, parental acceptance. And you see a little arrow over there coming out of PA, and that is really the star of the show for this presentation, and that is our residual error variance. So that's pretty much saying that everything else other than what's accounted for in this model or used in this model is represented for by that arrow, other things that could impact parental acceptance.
So the software we're using for this presentation is Mplus. If you're not familiar with Mplus, we've recorded in this series last year a presentation introducing people to Mplus. So you could go to the AQPS lab website and find on the events page a link to that presentation if you're unfamiliar with Mplus. If you're watching this on YouTube, there will also be a link in the description to this talk. But this is what the Mplus syntax looks like. And the important parts are that we're using the complete item level data, and also there's an ID variable involved as our data. So we need to create scale scores for each of these scales, parental acceptance and cognitive flexibility and so on and so forth. Those are in the define command. So we're not using a sum score for our variable, we're using an average score. And the reason for that is that structural equation modeling programs, whether it's Mplus or SAS or a state, they are not very good at handling variables that have high variances. So generally speaking, if your variance is, say, above 10, you'll want to rescale it to make the variance smaller. I think ideally you want a variance of around 1. That's optimal. And so normally we would talk about sum scores as being an observed score for a scale. But here we're using the average item score just because it works better with the program. Next up is the variables we're using in our analysis are those scale scores, those average item scores. And we define the model in the model command. It's really simple. The outcome on the predictors. So we're regressing parental acceptance on all of these other variables. Okay. So when we run that, we get output. Specifically, we're going to look at the standardized output. And there's two reasons for that. One is that it's more comparable across different studies. So if I did this same sort of study with a different sample, we wouldn't be able to compare our unstandardized coefficients, but we can compare our standardized coefficients. And the second reason is that these standardized coefficients are comparable across different models for the same set of data. So we're going to show you, this is the observed multiple regression output. We're also going to show you 3 other different models, and we can compare these coefficients across those 3 models. The most important one is the R squared. So this is the sort of an omnibus test for the regression model. It tells us how much variability is explained by our predictors. And we have 18.2% of the variability in PA is explained in this model, and that's significant. We have p-values that tell us the significance of our individual predictors. So we can see CFIC, DERS, RFS, and MGP are all significant predictors. And then their beta coefficients, the standardized regression coefficients, are shown here under estimate. So we can write up the results, talk about how we're explaining a significant portion of variance, and such variables significantly contribute to the model. Write that up, stick it in a publication, send it off to a journal where we get a review.
So reviewer number 2 says, this is all fine and dandy, but did you check your assumptions before using this particular model to run your regression analyses? And that made us say, we better check our assumptions.
So the assumptions of multiple regression are many. The ones of interest to us today refer to the perfect measurement of predictors and also the normality and homoscedasticity of residuals. There's a bunch of other assumptions, but they're not relevant to us today.
So what is perfect measurement, I think, is the first idea that's really important to think about here. And so perfect measurement would be that the observed score, that score you get for whatever the construct is you're looking at, in this case, parental acceptance could be an example, that observed score is equal to the true score. It's exactly the same. But in reality, a lot of times we're dealing with this imperfect measurement. We made these measures. They might not completely capture every aspect of the construct, despite all of our best efforts. And so our observed score is actually reflective of a combo pack between the true score and error. And so you have that true score and error variance and measurement error variance that are within that observed score variance. And so often when we look to the literature to get an estimate of how do I know what my measurement error is and what my reliability is, that alpha is often what is used to demonstrate this. It's certainly not the only option, but it's often seen. And so alpha is a way of letting us know how trustworthy our construct is to getting at the construct that we're interested in. And so you can see down here, these are the alphas for our study example, and there is a range between 0.7 all the way up to 0.98. Now 0.7 is really the bottom threshold that you are okay with using, but most recommend at least 0.8. But it's really important for us to stress that even if you have a good reliability, there's still measurement error that's in there, and it's still really important to account for it in the models that you're using.
So we're going to consider regression is explaining covariance, and so it's not each individual variable, but how they combine together and their covariance is important. So if we think about two different variables, x and y, they're composed of both, their total variances are composed of both true score variance, in green for the predictor, and purple for the outcome, and measurement error variance that's in orange. And we're going to see how that reflects on covariance. So again, the blue rectangles are the total observed score variances for x and for y, and the covariance is the shared variance. The variance shared between x and y is the covariance. So this is what it looks like in the observed world, and if we include measurement error in this picture, what's really nice is that measurement error is always assumed to be uncorrelated with everything else. And so the measurement error pieces, they don't interact with the covariance at all. The covariance between the true x and true y scores is the same as the covariance between the x and the y scores. So that's really nice, and that property is going to enable these corrections that we're going to make. Okay? But in the picture of the covariance between two variables measured with error, all of the covariance is between the true score variances.
There are multiple approaches for handling measurement error. One approach is to correct for measurement error, and that can be done by correcting the correlation matrix, which has some limitations. It doesn't handle missing data, and additionally, it can increase your type 1 error. Another approach that we'll be talking about today is the single indicator latent variable approach. And this is great if you have low ends that you're working with. And then the best approach is to account for measurement error using structural equation modeling. This can sometimes be limited, though, if you do not have a large enough sample to run a SEM model.
So the first model we're going to show you how to work with is a single indicator latent variable model. So the slide is about what is a single indicator latent variable. And here in green is, throughout this talk, green represents true score variance for a predictor. Blue is observed score variance, and orange is measurement error variance. So X of L, L for latent, it's a single indicator latent variable. It's a latent unobserved variable, and it is indicated by the observed variable X. So it's a latent variable, just like any factor and effector modeling. And it only has one indicator, which is X, which causes identification problems. And we'll fix those in just a moment. And the disturbance D, the error variance of X, it captures the measurement error variance. So the notion here is the measurement error variance is going to be set to the, whatever the measurement error variance is, the variance of X times 1 minus alpha. And then the rest of the variance of X is all true score variance. And when we set the loading of X onto X of L at 1, that ensures that the variance of X of L is a reliable variance of X. So when we use this structure to create a single indicator latent variable for X, we assure that X of L, the latent variable, has the same covariance with everything else in our model as does X, but X of L has the appropriate true score variance of X. Okay. So how does this work in a regression context? I'm just going to show you simple linear regression. This is with observed variables. We've got X and Y that have their own variances. And the path coefficient between them, the regression coefficient, assumes perfect measurement in both X and Y. So we could compute a reliability. We're just using alpha here. There's a lot of different ways to estimate the reliability. We're just pretending like alpha is our reliability. We can compute an alpha for X and for Y. So if alpha is the reliability, then alpha times the observed variance will be the reliable variance. And the observed variance times 1 minus alpha will be the unreliable part, the error variance. And so the problem with this model on top is that it's not any way accounting for this measurement error variance. It's not anywhere in that picture, so we end up with biased coefficients for B. So I'm going to give you, this is the same example, I just made up some numbers. Okay? So there's nothing crazy going on here, I'm just putting in numbers so you can see how all these computations work. If the variance of X is 1.4, and the reliability is 0.85, multiply those, 1.19, that's the reliable variance. And multiply the variance 1.4 by 1 minus the reliability, get 0.21. That is the measurement error variance, the unreliable variance for X. Okay? So those are how those computations work. And we're going to use those values in our single indicator latent variable approach. So if we want to do simple linear regression with single indicator latent variables for X and Y, the regression coefficient is the coefficient of the path between the latent variable for X and the latent variable for Y. So on the left, we have this block. Okay, we're modeling X as a single indicator latent variable. On the right, we have another block. We're modeling Y as a single indicator latent variable. And then the variables that we use for our structural components for the regression part are the latent variables. And so we can see down below the variance of each piece in this model. The measurement error variance for X is the D over on the left, has the same formula as the previous slides, and the D on the right, same formula. So each of the variables has the corresponding variance indicated here. And we computed all those for our example, and they here are the variances for our empirical example for all these different pieces. And now this coefficient B between the latent variables is being corrected for measurement error because the measurement error is in the disturbances, not in the latent XL and YL.
So this is what that single indicator latent variable model would look like. Again, very similar to that first model, but instead of using just the observed variables, we're now incorporating those latent variables and incorporating those disturbances, the measurement error, on the side as well, both in the predictors and in the outcome variable. And so this is what your syntax would look like in Mplus. So you'll notice here, David just went through all of that math, and that's actually going to be specified in our model right here. So single indicator latent variable approach, the way it works is that we are specifying a number for our measurement error so it can be managed in the program. So you specify here doing the math that David just did with your variance, and then you, down here, you're going to use the latent variables in the regression command.
So here are the results from that analysis, and a little bit different from the results for the first analysis with observed variables. R squared is a bit higher, and one thing you'll see under the R squared part of the output is all the observed variables, PA through MGP, they have a R squared, so this is the amount of explained variance, and these are exactly equal to the alphas. Okay, so how much of the variability is explained inside the model? That's alpha. Okay. And then in the standardized results, we've got a whole bunch of these with statements. These are the correlations between the latent variables for all of the predictors, and you can go ahead and ignore those. Those correlations don't appear in the output for the observed variables. You can ignore them here. And then also we have p-values and beta coefficients, just as we did in the previous set of estimates.
So we can see here just a comparison of our observed model versus our SILV model. And you can see that the R squared has changed pretty largely. And additionally, we have a change in significance for one of our variables. So there's some differences between the models when you are incorporating accounting for measurement error. So we've been talking a lot about measurement error, and measurement error is really tied to this concept called residuals. And residuals is really just the deviation between your actual value that you are observing in y and the predicted value of y, since the linear regression equation predicts a regression line. So that difference is what we're interested in with a residual. And they're assumed to be normally distributed with constant variance among the predicted values. And this is going back, the residual piece, to those assumptions that we have when we're conducting a regression. And so this is what a plot of residuals is supposed to look like. You'll notice that it's kind of just a blob with no particular pattern to it. And that's indicating that there is homoscedasticity, that there's nothing going on with the residuals that would be worrisome. However, in our model, this is what our residuals look like. And this is a really great example of something called heteroscedasticity, where residuals are distributed differently for the predicted values of PA. So you can see here that there is a decrease going on with our residuals across PA. So that is an indicator that something important is going on.
And in particular, the important thing that's going on with this data is censoring. So censoring is what happens when there's a maximum possible score. These items were Likert type items, so the most you can do is strongly agree with all of them. So if you strongly agreed with every PA item, you get the maximum score. And a whole lot of people got the maximum score. Everyone whose residual is on this line, in fact, got that maximum score. So if you think about what if it were possible to get higher than the maximum, if you have a high predicted score and you got the maximum score, well, there's a very small residual. But if you were able to get a much higher score, then the residuals could be large and positive. So again, if your predicted score is high and your true score on PA is very high, then you'll have a large residual. But if you're not capable of getting that very high PA score, you're only capable of getting the maximum PA score, it means that those residuals are smaller the higher your predicted PA is. The effect of there being a maximum possible score that we can't go higher than, it's called censoring. Everyone who would have gotten a higher score they get the maximum score instead. Danny's going to tell us a little bit more about how censoring works.
So censoring works, like David's been saying, when a lot of people are getting that maximum score. So if you look at this table, all of those people by that arrow got the maximum possible score, as opposed to when we think about the normal curve, that there is kind of a bell situation, even if it's skewed, that there's a bell. In this case, we are just chopped off at that highest score. And so as another example, this is not related to this particular project, if we think about scores on a math test. Math ability score is normal in the population would have this lovely bell curve situation. But if we give a math test and it's too easy, we're going to get a lot of people with a perfect score. So instead of getting that lovely bell curve, we're going to get this censored effect where people are stuffed at that maximum score.
So the question is, what can we do about that? Is there a way to handle censoring in our regression analysis? And the answer is yes. We can use something called Tobit regression. So I've created some simulated data here to illustrate the problem of censored data on regression. So here we have uncensored data. This is just perfectly fine data for x and y. There's a regression. R squared is 0.44. The slope is 0.88. But what happens if I cut off the y value, so censor y and say, hey, the maximum score you can possibly get on y is 30. So every point above that line, y equals 30, is going to get squished down to y equals 30. What happens? Well, the regression model looks very different. The R squared is quite a bit lower, and the regression coefficient, the slope, which was 0.88 before, is now 0.58. So it's biased downwards. The intercept is biased upwards, and R squared is biased downwards. So we're getting biased results. This is bad. We need to correct for this somehow. And there's a technique called Tobit regression that does that. It creates a latent variable, so we don't get a picture of it, but it creates a latent variable, assumes a normal distribution of scores in the population. So that's a big assumption. People are going to normally distribute it from this latent variable. The observed variable is created by making a cutoff on that latent variable. So it's latent. We don't get a picture of it, but when we use this technique, we see that the R squared is actually very similar to what it was originally. Under ideal circumstances, on average, Tobit will perfectly address censoring, but in any particular instance, it'll get close. And no statistical technique is absolutely, totally perfect.
And so for the Mplus output, this is what the combo between Tobit and SILV would look like. So the first thing we're going to do is declare PA as censored to invoke Tobit. So that's all you say. Censored is, and you say your variable that is censored. And then additionally, we have a little A in parentheses. And that is an indicator that for this set of data, it is censored strongly from above. If it was censored from below, then we would put a B. If it was censored both ways, then we put a C. And we also notice that because we are censoring PA, we are no longer using an SILV correction for PA in this particular situation. And then PA down here is predicted by the SILVs for the other variables. So we're still doing SILV, it's just for all of the outcome, or the predictor variables, rather. And this is our output. So again, we're still using those standardized results, always the standardized results. And we can see down here we have our R squared for PA, still significant, and it is now 0.2. Our p-values and our estimates, and things are slightly different, but not significantly different. And this is a comparison of our models, and you can see down here the R squares again have changed somewhat. From that observed model. There's still more variance being accounted for with these different correction approaches. And I think it's also, I wanted to note, I realized we didn't say this, that the censoring effect can be created from things related to measurement error, such as not having the items have enough options, response options, so it could be related to measurement error, but it can also be influenced by other things like your sample being largely, in my case, parents of LGBT children that were very accepting. So there's lots of different things that can create a censoring effect that Tobit would be helpful to manage.
So we had these two different approaches, the SILV and the Tobit approaches, to handle the measurement error on the PA variable. It's natural to ask which approach is better. Well, and they have different assumptions. In Tobit, we made that assumption that in the population, the distribution of scores was normal. So if that's not true, then the Tobit model will not give accurate results. The SILV model, on the other hand, makes an assumption of homoscedasticity, by which I mean that the measurement error is the same at all levels of PA. And also that after accounting for the measurement error, the regression residuals, so back in our model with the single independent linear variables, the regression residuals would be normally distributed, would be homoscedastic, which, if you have censoring, is probably not an appropriate assumption to make. So for our particular situation, the Tobit approach is probably more appropriate because we can't meet the assumptions of our SILV approach. But if you think, hey, after I count for the censoring, I probably do have homoscedasticity, you can use both of these techniques at the same time. You can declare PA as censored and also have it load onto a single indicator latent variable. But in order to do that, you would have to be able to predict the amount of measurement error, which is not an easy thing to do. You would need to have, from other studies, you couldn't do this inside of our one study here, be able to accurately determine the reliability of PA when it's uncensored. So if we use it in a similar population, but in a just slightly different enough that there wasn't this strong censoring effect, and we could estimate the reliability, we could use that information to additionally incorporate SILV into the Tobit approach. But it's natural to ask, is there something even better? And yes, there is something even better. Structural equation modeling is a more appropriate way to model this relationship. So the full SEM model, it has individual items in the model that are indicators of latent variables. So instead of having the sum score being an indicator of a latent variable, each item will be an indicator. Furthermore, in an SEM context, we can treat the individual items as categorical. So if you think about the sum score being strongly censored, each of the item scores will also be strongly censored. Because remember, everyone who got that maximum score, they got the maximum score in every single item. But when we treat the items as being categorical, that's not a problem. All it means is that the population had a score distribution that means, well, of course they answered them, strongly agree to all of them. So it's a robust way of explaining that censoring, and it's going to do a better job of handling it than Tobit will on the PA variable. And finally, when we talk about our previous methods, the SILV method, it corrected for measurement error, which meant that we had to specify in the model the amount of measurement error, and it made correction based on our specification. Whereas in structural equation modeling, the measurement error can actually be accounted for, which means is modeled inside of the SEM. And so because of that, it can be more accurate in accounting for measurement error than our other techniques. So what does an SEM look like in a regression context? So our full model is very complex. So I want to show you a small model first. We're using the same variance labeling scheme as before. Orange is measurement error variance. Blue is observed score variance. Green is true score variance of the predictor, and purple for the outcome. So the predictor, X, is it's composed of 3 different indicators, X1 through X3, that load on X of L. And each of those indicators, each item, has its own measurement error, the disturbance D, that can be estimated inside of this model. That's the big difference between this model and the SILV model, is the extent of the size of those disturbances is estimated inside the model as opposed to specified by us. And the outcome X of L works the same way. I have 3 items loading onto it. They each have disturbances. And again, there's still that unexplained part of Y. X is explaining Y, but there's some residual variance to Y That's that little arrow leading off to nothingness.
But David, are these different instruments for X1, X2, X3, or is it something else?
So those would be individual. So if X, for example, was CFIC, which actually does have only 3 items, those would be CFIC1, CFIC2, and CFIC3. The individual items that are on that scale load on the latent variable for that construct. So when we get to this slide, it would be too complicated to show you the entire picture with every item and every disturbance. It would be hundreds and hundreds of boxes, and I don't want to draw them all. And it would be impossible to see them all anyway. So that circle, or CFICL, that's a latent variable, a factor upon which all of the CFIC items are loading. So there were a total of somewhere around 60 items. So partitioned properly, are all loading onto these individual items. It's a pretty large model.
And so this is the syntax for doing SEM in Mplus. As David was saying, you'll notice here that all items are included in the model. And then for our Likert type items, we're going to actually be able to specify here that they are categorical. And categorical meaning, like when we think about a Likert scale, that there are ordered categories, we can now actually incorporate that into the model here. And we're just going to specify PA on, CFIC, and so on and so forth.
So those are the latent variables in the regression part. The on command is between the latent variables that are measured by individual items.
And this is our standardized output here. We have our R-square. 0.32 is where we're at now using the full SEM model, and it's significant. And then we still have CFIC and DIR. Now DIRS is significant again, and it had gone off significance in one of the former models. It is now significant. And then RFS and MGP are also significant in this model, and we can see the beta estimates here.
So when we compare all the models, a few things should jump out at you. One is that from the first observed model, the last SEM model, the coefficients tend to be larger. The non-significant coefficient for CFIA, it just kind of bounces around a little bit. But the R-squared in particular, the SEM that's able to account for all that measurement error properly, it has a much higher R-squared than the observed model does. And that is, that's generally true for latent variable models. They tend to have higher R-squareds. That's not the reason to use them, because just because a model gives you a stronger looking result doesn't mean it's a better model. The reason to use them is that they are a better model. But if you're needing some extra motivation to go through all that extra work, having a stronger result certainly doesn't hurt. We expect not only to be more accurate, but also be more sensitive, have better power for detecting the significance of these coefficients and R-squared. And also, some of the values jump out at you. The coefficient, the standardized regression coefficient for RFS is substantially stronger in the SEM model. And that is generally observed in the literature, that SEM models are not only more accurate, but they're also more powerful and tend to show larger effect sizes because of their additional accuracy. So, what should we get from this? Well, the first thing is that, looking back to this table for a second, if we believe that the SEM model is as close to truth as we're going to get, the observed model, these coefficients are very different. So, the measurement error can bias ordinary least squares regression for underestimates, which will invalidate your hypothesis tests. Their type 1 error rate is not what you think it is. So, when we have measurement error and we do standard observed ordinary least squares regression, we get results that aren't trustworthy. That's bad. So we have modeling techniques that we can use to estimate and handle that measurement error, minimize the bias. If you have a large enough sample size and appropriate sorts of data, you can use structural equation modeling, which is always preferred. If you have smaller sample sizes, you can use a single indicator latent variable approach, which wasn't a perfect correction, but it was a lot more accurate than the observed scores. And finally, we end up with greater validity the more accurately we can model what's really going on with our data.
And so the big picture we really want to have you take away is that poor measurement and not doing all of the extra work, and we recognize that it is extra work, but not doing that extra work is an ethical problem, because if our measurement is problematic, the reliability of our findings is compromised, and so we can't trust the results that we're sharing. And since we're doing work that we're trying to improve our understanding of concepts and constructs and relationships between things, it's really, really important that we do whatever we can to make our results trustworthy, so we're contributing to the literature in a way that is impactful and ethical. That's all, folks.